It's my honour to introduce and welcome Peter Zoller, who was involved in laying the theoretical foundations for two of the three major experimental platforms that we heard about yesterday, ion traps and Rydberg atoms, and also in the context of analog quantum simulation was proposing using cold bosonic atoms in optical lattices, also back in the 1990s and since then. So thank you very much.
So let me first of all thank the organizers here. This is the students at Postdoc Council that invited me here. It's quite an honor to give two lectures here. And I was also given a title, okay, and the title was Experiment Meets Theory. Maybe I should, from my point of view, say theory meets experiment. And I was also given, analog quantum simulator. I allowed myself to add here the word programmable to the whole story, because without programming, the whole thing gets sometimes a little bit boring, I would say. So it allows one to actively program quantum devices, and this is really what we'd like to do. So I have to say that for me personally, things have changed a lot during the last 30 years, in the sense that I was one of these early birds that thought, I don't know, 25 years ago how we could build some of these quantum devices, and be it from quantum computing, like with trapped ions, or optical lattices, Rydberg atoms, and so on. We thought a lot about also polar molecules and so on. But this was sort of coming from the atomic physics background, and how to build engineered quantum antibody systems that we run as quantum computers or quantum simulators. But sort of times have changed now, because my experimental friends, they built these devices in the lab, and now they are coming back to us as something that we can play with. And this sort of experiment meets theory reflects, I think, very precisely what's going on. So in this sense, I will speak in the following about me as theorist, thinking about the experimental possibilities that we have today in the lab, the devices that we have, and then what kind of interesting things can we do. Of course, this always comes in two flavors. You can try to do something that maybe falls more into the category of what I would call basic science, basic quantum science, and this is really what my talk will be about in the following. It will be talking a lot about entanglement and how to measure it. Of course, we should also have in mind applications, and maybe at the end I have a few minutes to say about these programmable quantum simulators that act as programmable quantum sensors, as one of these examples along these lines. So the playground, I mean, it's sort of listed over here, and I just can say that, well, I initially had prepared sort of, a little bit more explanation about some of these, ions, optical lattices, Rydberg, but even the fact that yesterday we had a whole day that explained about different platforms, and I really emphasized that what I will talk about on the theory side may be exemplified with trapped ions, but really the whole protocols and what I talk about in the whole bigger picture applies to really all of these systems over here. So I don't really have to say much, because all of you are already experts in the field now. You know everything about ions, maybe optical lattices, we haven't heard so much, but definitely about Rydbergs and so on. And superconducting is sort of an honorary member, I would say, of the atomic physics community, because these artificial atoms are pretty good atoms in the meantime, I would say. So this is sort of setting the stage, and the reason why I fell in love with these programmable analog quantum simulators is that they are typically scalable to large particles. We always think about quantum advantage, and scalability is essential. And there's some amount of programmability that you can, program these devices to ask interesting questions, even though it's not usually at the point of being a quantum computer, even though I somehow see a continuous spectrum. I think that Ike Chung mentioned this yesterday. We have analog simulators, we have quantum computers, and what we're doing at the moment is sort of walking from one end of the spectrum more and more to the other one, and you will see this happening in the talk over here. But scalability and programmability are sort of key features. So I decided to focus on the topics that are related to this sort of maybe more basic science. I speak about learning protocols to reveal, I emphasize here, large-scale entanglement structure of many-body systems. This is something that has been very close to my heart now for several years. We talk about entanglement entropies, entanglement Hamiltonian, how to measure them in the lab. and hopefully see very fundamental and basic features that we expect to see in all of these quantum simulation systems, one or the other way. And we have different protocols for doing that. I will talk about randomized measurements as we do it, give you an early example, and then talk about things that we're doing at the moment right now. And all of this is done with atomic disk devices. This means that we're not talking about error correction and sort of the usual kind of circuit. Pictures are, for me, at the moment, more in the background. There's something in the future where these things will develop to. So, what is quantum simulation? Well, quantum simulation is that we have some many-body system, we write down the Hamiltonian. We can do, of course, classical computing, which is not what we want to do, because we would like to have some sort of quantum advantage, whatever it might be at the end. And then we build analog, digital, or maybe hybrid quantum simulation devices, and we already know a lot about these things from these previous lectures. As I said, the frontier that I would like to talk about is this, that, why do we have a quantum advantage, and why do we think that these quantum devices are important? It's all related to entanglement, and this is this symbolic, picture over here, that if you get a many-body system, think about spin 1/2 or qubits, they can be in the superposition state, so a huge entangled state that can be in principle exponentially large. And this is really what gives the power to these devices. And so the question that we're going to ask now in the following, this will be the theme going through all of this, is that we would like to learn about this entanglement structure of the many-body wave functions that we have here in quantum simulation. And we are interested in particular in protocols that work for large particle numbers. I will say that this is the sort of large particle number frontier that we have at the moment in the entanglement. And then you might say, well, what's special about quantum simulation in this context? And the answer is actually very simple, that the Hamiltonians that we have in many-body physics, they are Hamiltonians that have, they are what we call k-local. Like, for example, this would be a Heisenberg Hamiltonian over here. And they have two-body interactions in this form over here, not three-body or four, or maybe infinite number of interactions, or as large as the particle numbers. So they have usually a very, very simple structure. And the wave functions, the entanglement in the wave function that we will encounter in our quantum devices, if you do quantum simulation of a many-body system, inherits, some of the simplicity of these Hamiltonians that actually generated these wave functions here in the first place. And this makes it a special, problem, because on one hand, quantum simulation is very important. Entanglement is the key ingredient, but it also gives us the opportunity, because it's somehow simpler than the generic entanglement in general, to learn something about this many-body wave function over here and the entanglement structure with protocols that are sort of tailored, taking into account that we talk about quantum simulation problems over here. We want this, of course, all to be valid in the regime of large particle numbers. Of course, you can, if you've got a very small system, always do tomography, but we would like to go beyond, but we have to explain to what extent we'll be able to do that, okay? So here's sort of an outline. I wanted to start out with an introduction, a little bit background on programmable quantum simulators. I can make this part very short, but I will now use it rather demonstrating you what can be done in the lab at the moment in terms of preparing interesting quantum states that in the following part of the talk will be the playground where we then would like to investigate, for example, entanglement structure. And I have a second introductory part over here. I have to tell you a little bit about how we characterize entanglement in these many-body systems. These are these things like, what's an entanglement Hamiltonian, with a Schmidt decomposition. We have an entanglement spectrum. Why do we care about all of that? Sort of setting a little bit the stage of what kind of things we would like to see and measure in the lab in the context of many-body simulation. And, excuse me, over here then, which is supposed to go back here. Okay. And then, of course, the central question is how to measure this entanglement here. And some time ago, I fell in love with these randomized measurement toolboxes, and I will sort of start maybe a little bit historical, telling you the ideas that came from our side, with this entanglement Rayleigh entropy, but at the end really switching over to sort of maybe more recent and also more interesting things like doing entanglement Hamiltonian tomography and all of that. And I just want to point out that we wrote the review together because this randomized measurement toolbox is very much related to the classical shadows that were introduced by, for example, John Preskill and his friends. And they sort of came from different sides, and these things are related, and I will tell you sort of the story a little bit how we encountered it, which was sort of very much coming from this experimental side. Well, this is the zoo of things that all of you know. I mean, you talk about here programmable analog simulators, and I mean, I put down here a few examples that come from Rydberg's to Hubbard models. Superconducting circuits are, for me, one example that belong over here. And of course, trapped ions. In Innsbruck, we have the fortunate situation that Rainer Blatt and his team are just down in the basement, so we can talk to them a lot. And these machines, often if you have good ideas and you convince them, are available. It comes as, for example, these 51 ion strings that I will show you afterwards, which is the playground, has existed now for a few years, and we're allowed to sort of, under quote, program these things. But I also want to emphasize, but we don't have any results of these things yet, that Christian Roos has built now 2D arrays with these ions. He has sort of setups that has, for example, 90 ions that show all of the features that we know from the simple string of ions over here, like that they have long range, for example, transverse Ising model, and so on. And I would say that this should become a playground now in the following. Going to 2D in the context of the ions, I think, is something very, very important. And again, in this context, to repeat my question, we would like to learn the large-scale entanglement structure of many-body quantum states that we prepare in these devices, and my focus will be on the experiments down here. But really, everything works for all of these systems over here with their own plus and minuses that we have. So to develop a tool set, okay? And here's, of course, what you heard yesterday, and I just have really one slide on this thing, and then we got going on what we really want to do. Yesterday you heard Hannes Panin gave these very nice lectures about Rydberg Fries arrays, and he wrote down Hamiltonians of this type. I don't have to explain much here anymore. You can see that this is a spin Hamiltonian, Rabi frequency over here, some detuning, and then we have this 1 over r to the power 6 interactions between the Rydberg states here. And they can in particular also not only be 1D, but also 2D. And we have ions over here. Chris Monroe gave, I think, a great talk yesterday explaining, where this Ising Hamiltonian that I'm writing down here with this long-range interaction is coming from. Again, this is a string of ions here just for 20, but then we have 51 at the end, which is our playground. And we have then, of course, in addition to all of that here, for example, laser beams that can address all of these ions over here. One hand, well, maybe reading it out, but you might also here simply do single qubit rotations. In principle, this is a fully programmable device, but we will operate it in the regime in the following, where it scales very easily, like these 51 particles I mentioned, and now Christian Roos has 90, and probably can do all of these things, in the same way now in the 2D setup, where we have sort of the native Hamiltonians, this Ising model down here, and this would be the native Hamiltonian over here. So what's good about these things? Well, I mentioned it before. The unique features are that these things scale, to a very large number of particles, in the way that these Hamiltonians that we write down over here, they can be realized with very high fidelity, and but in general they have programmability also, in the way that we indicated over here, but possibly in a reduced form. And this is setting the stage, or the playground of what we would like to do in the following. We would like to have large particle numbers and then explore certain things like this large entanglement frontier, for example, based on these existing devices that we have right now in the lab, and we would like them to develop protocols. This is the lab here, It means that I'm good friends with experimentalists that give me these very nice pictures over here. And in the good old days, when people were taking ions, for example, and doing quantum simulation experiments, I remember that Chris Monroe was the first one to actually build one of these trapped ion simulators. The notion was always to do somehow quench dynamics in some form. And you can see that I find this interesting in this context, even in this old version, because here you can see out of product states, due to the quench dynamics over here, you have entangled states for a very long time. You would expect that subsystems over here become thermal states. So entanglement comes in over here, but this is the way how we can measure these devices. You take individual shots over here and some computational basis, building then somehow, hierarchies of different probabilities corresponding to the different bit strings, which allow us to give, for example, expectation values, whatever you would like to have. But we would like to program these devices now in a sort of a very natural way by just going back to the native Hamiltonian provided by the system. In the case of the ions, this would be the Ising model over here. And you might then immediately write down something that's sort of in between the normal analog simulation where you have a quench, but you put down here actually gates, you know, that are huge entangling gates. So we have basically entangling gates provided by these native Hamiltonians that are very large particle entangling gates, and you can usually, they're scalable, you know, to very large particle numbers, and they can be realized with very high fidelity. The sort of downside is that very often it turns out that you don't really know precisely what these Hamiltonians are. In the context of ions, for example, you know, if you got a little bit of a misalignment of your ion string, you might find out that these couplings that we wrote down before, this J, they have little bumps that you might not see. And so there's, you know, it also comes with a cost. But we'll see afterwards, you know, when we do variation algorithm now in the next slides, that actually you don't really have to know these things. And so the scalability, if you combine it with the right algorithm, then also is sort of a very good answer to come around some of these difficulties. Of course, you can always do Hamiltonian tomography and learn the Hamiltonian that we have over here. And based on that, sort of, you know, proceed as we do now. So very clearly, you know, when we have something like that, we can produce in the lab just, you know, a family of entangled states over here by just, you know, taking a sequence of these native Hamiltonian gates, maybe single particle rotations, another one that is switched on for different time. It generates a family, and this is sort of programming highly entangled quantum states from available quantum resources. And this comes sort of free, and this can be done with very high fidelities. So it can be interesting if you're programming in this sense here, interesting quantum states, a family. At the moment, they don't have any deeper purpose over here, except that we can see that we can do that. And in the case of the ions, of course, you know, it's exactly the toolbox that Chris mentioned yesterday. We have these entangling Ising interactions here and the local rotations. So again, I mentioned they're scalable and they're robust. Again, you know, these quantum algorithms that we will now write in the following, against not knowing precisely what these Hamiltonians are. We just know that we can reproduce them, but they might have certain unknown factors in there, like maybe the coupling is slightly different or have little bumps or whatever, but this will drop out once we go over then to running, for example, programming in the quantum simulators in the sense of doing then variational classical quantum algorithm. I have to say that I fell in love with this variational classical quantum algorithm essentially because of the robustness behind this thing. You know, you don't have to know the details. You have your huge entangling gates that come with a very high fidelity. You might not know them very precisely, but once you're doing variational quantum, classical quantum algorithms where you run on a feedback loop optimizing a certain cost function, you're optimizing a cost function, and you might not know the details of what's really behind all of these gates, but in the end you get the answer from optimizing the cost function that you want. And because all of you, of course, are very familiar that when you write down here a cost function, this will be a functional of the wave function that you generated on your quantum device over here. This cost function that you write down is optimized on the classical machine with a certain number of variation parameters that correspond to how long you switch on these various gates over here and so on. You're very familiar with that, of course, from the quantum chemistry context. And while the right-hand side is evaluated on the quantum machine, and the hope is that we can do this more efficiently than we would ever be able to do that. In 2D, for example, this is very clear. If you take a PEPS, for example, the contraction of all of these things would already become very expensive. These things sort of matter. And of course, the prime example, but this is of course only one of them that again you have seen 100 times, I guess, is this that you do the variation quantum eigensolver in the sense of optimizing energy, where this quantity over here is now the energy to be optimized. You're trying to find ground states. And the game that you play over here is this, that you write down a certain Hamiltonian over here, that you specify and just write down these things here for spin Hamiltonians, but for other systems like Hubbard models may be a little bit slow in the context here, but that you can just write down here Hamiltonian, which is the target, and then you can ask, given the variational set of wave functions we generated over here, let's try to find the minimum of the cost function, the energy, and then find an approximate ground state. And this Hamiltonian that we write down here is never physically realized. What's physically realized are these native Hamiltonians that produce these entangling gates over here, and we optimize in this sense for these quantum states, finding approximate states. So this is a well-known old story, but it really works well. So I want to convince you now the following. If you have, for example, say trapped ions as one of these programmable quantum simulators, and the same, of course, applies also particularly to the Rydberg arrays. So if I go back in time, a few years ago, we wrote papers where the topic was that we would like to simulate lattice gauge theories. We took an example, a Schwinger model. This was in 1D. It's an example of quantum electrodynamics. You know, that you put on the lattice. It's a lattice gauge theory. You add here matter fields to the whole story. And at that point, we had sort of, 20 qubits, and now we have sort of 51. And the kind of things that we learned during this time was that when you make 10 to 5 calls, you allow 10 to 5 calls to the quantum machine. This is a number of experimental runs, sort of dictated by an afternoon, or maybe then the lifetime of your graduate student over here. You don't want to have something that takes forever. And you build then certain gates, and then you play the game of writing down then, for example, the cost function, trying to measure the cost function. For us, this was a learning period, and what we did then, if I just summarize, because now we're going to move on to sort of more interesting topics over here, was that we said, well, on the physics side, let's write down a lattice Schwinger model, quantum electrodynamics. I'm not going to talk about lattice gauge theories here per se. The fermionic matter field, the quantized electromagnetic field. But the 1D situation is actually very simple, because this quantized electric field that you have over here, this is 1D, so there's no actually no magnetic field here, allows you to write down at the end of the day a spin model, which was very complicated, but you can ask your device to solve it. And what we developed during all of this time was then these classical optimization algorithms. We called it here the dividing rectangle search, that we had to modify from the literature, because it was a global optimization in a noisy landscape. But at the end of the day, we improved, relative to our first attempts, our, the run times that we have to do by a factor of about 50. And if we have an experiment, a factor of 50 very often means yes or no being able to do these experiments. So I'm simply saying that there's a lot of technology behind these things. These things were developed, and just to give you an example over here from these old days, this is an example how you iteratively approach here the ground state of the Schwinger model. This is the first excited state, and you could measure the first excited state and the ground state. And I guess one of the highlights was, we call this thing self-verifying quantum simulation, you could also measure the variance of the energy. So you measure the energy, but also the variance on the quantum machine. So in this sense, the quantum machine gives you, that's the energy of the ground state, but also the corresponding error bar. This was one of the highlights. So then, this was with 20 ions, but let's now move on, and I'm setting the stage now for producing interesting wave functions, where I come back to my actual topic I would like to discuss, which is how to measure entanglement in these systems over here. So suppose that you sort of wake up one morning and say, well, today my target Hamiltonian will be the Heisenberg model. Why the Heisenberg model? Well, you will see afterwards that it's an interesting model, because it sort of is related to conformal field theories, and there's interesting entanglement properties over there that we're going to investigate afterwards. But if I ask the trapped ion people to realize directly a Heisenberg model in the way how it's written over here, this would be very, very difficult to do. I mean, I would not know how to do that, but of course in variational, you can just write down this, target Hamiltonian over here, and you can then cook up circuits, and this cooking up of the circuit over here, we want them to be very short, and we don't really want to go to the real ground state over here. For the following physics, it will be good enough that we are close to the ground state. And so we cook up certain circuits over here, and I think there's not much point in trying to tell you what we do exactly for the Heisenberg model on. I just tell you that there's this sort of playing between theoretical simulations, the way we can do DMRG. For 51, ions becomes very, very expensive, but we do it for smaller numbers, and we go to the machine and try it out if it works over there. So we can sort of iteratively between theory and an experiment develop here quantum circuits that give you well, pretty close to the ground state. Let me show you what comes out here for 51 ions, where we are definitely not in the ground state, but to give you a feeling for what's going on. So this is 51 ions. We write down a Heisenberg model as our target model. We have a relatively short depth circuit, so decoherence does really play a role. We do our optimization on this whole thing, and at the end of the day, what we're able to achieve over here is a situation where 51 ions, so the Hilbert space is about 10 to the power 14. We prepare something which is an approximation to the ground state of being a superposition of maybe the lowest few hundred eigenstates, out of 10 to the 14. So we are definitely not in the ground state, but for the physics that we will discuss now in the following, it's also not so important, because we're not after properties are the entanglement of the ground state, but for this to be physically relevant, you really want to focus on the situation where we would like to find entanglement properties of something of maybe the first few hundred states. So typically you get something like 2% of the total spectrum. If I take my Heisenberg model, there's a ground state, there's a highly excited state up there, and we can prepare with these short depth circuits with 51I something like 2% down here in this energy range. Pretty good. If you want to go for the ground state, okay, we can't do that, but 2% is already not so bad. So this is sort of setting a little bit the stage, and these are pure technology statements that I'm making over here, which is now the starting point for what we actually want to do, because I will now in the following ask the question that, well, we got an interesting model over here, and today we took the Heisenberg, maybe tomorrow we take something else, but we can do something very similar then, so take this as an example. 2D, of course, would be much more interesting if you had on the Rydberg array, for example. This could also be done immediately in this particular form. We would like to study now entanglement properties, for example, of states that are the ground states, so let's sort of formulate this more loosely, of states that are sort of close to the ground states, in the low energy regime.
Can I ask a question?
Sure.
But in this way, I mean, you're not implementing a Hamiltonian, you're implementing a circuit that finds ways.
Right, exactly. So, I mean, and this is exactly what I mean by this programmability, Today you decide it's going to be a Heisenberg model because I'm excited, maybe tomorrow I'm excited about something rather different, and I write it down. And then it's always a little bit this magic of finding the short depth circuits that you have over there. But I would say that, this is rather flexible, and programmability in this sense, and the great thing about VQ is this, that you can just change from one model to the other one that you find interesting, and I decide now that Heisenberg is interesting because you see it's related to conformative theory.
Yeah, I was just wondering, so in the ansatz that you have for the ansatz, you don't seem to include a term which lowers the energy for the ZZ part of Hamiltonian.
Okay. So you're asking me, explain to me why this circuit works.
Kind of, yeah.
Okay, and that's a very good question, and my answer is that half of it is magic, half of it is a lot of playing around in details. Let me just emphasize one point over here. The entangling Hamiltonian that we get natively from the ions, I mean, Chris explained this yesterday, they have this 1 over r to the power alpha. Alpha, in the case of here, something like 1.2 or so. We have long-range interactions. Okay, and the long-range interactions that we have in there is not a gate between two adjacent ones, but they're really long-range. They are essential for the circuits over here to work. Okay, and the rest would be now a lot of details. Why does this thing work and not others? There's a lot of numerical playing around, and so let me just leave it by that for the moment. Okay, but I emphasize the importance of long-range interactions in the native Hamiltonians to get entanglement sort of far away very efficiently. And the way how you actually write down these kind of things that don't seem very obvious at all, I would say, is this, that you write down all of the commutators, and then you see that the commutators that you have from all of that generate sort of the right terms that should appear in the Hamiltonian up there, and this is then this sort of semi-experimental playing around to find the corresponding circuit. But our aim is not to find the best ground state approximation. Our aim is that we would like to go very low in energy, because at the end we want to ask questions that are not ground state entanglement features, but are valid in a low energy regime. This is a much more physical question than only ground state by itself. Okay, so having set the stage now, this is what can be done in the lab, and now you can say, let's now do something which is now, for example, basic science, in the sense of asking, can we learn about the entanglement structure? So I would like to show you now a little bit part over here where I will define now basic notions of how we characterize entanglement and what we would like to see in the experiment, what we're really after. And you can see that this will come sort of in different stages over here. The highlight at the end will be a complete tomography of the entanglement Hamiltonian for the total system being 51, and subsystems can exceed 20. Don't think about doing a tomography ever for 20 particles, it won't work. Okay, so imagine now, and of course I'm drawing here a 2D system. Ions are only 1D, but as I said, it also works for Rydberg very clearly. Suppose that you prepared now an entangled state of the system over here, and for the moment think about this thing as being the ground state or the approximate ground state here. What we want to do is this, that we would like to divide the system, which we assume to be completely isolated, into two parts that we call A and B over here, or sometimes also call it A and A bar. And we can define over here a reduced density matrix, which will be the central object of our studies now, the following. And when we write down this density matrix over here, if psi was just a product state, then of course the reduced density matrix by itself would also be a pure state. But you can see that this second order Rayleigh entropy, like the purity that we have over here, would already be one quantifier that tells you if this thing is a mixed state over here and the purity is less than 1, this is already an indication of entanglement. It will be sort of the most simple-minded things that we will do now in the following first. But you might also write down like the von Neumann entropy. You can see that this will be sort of easy to measure, and for this we have to work at the end much harder. But these are kind of sort of single number quantifiers of entanglement entropy that we would like to see then afterwards. And you might immediately ask, how do we measure them? And if I see the von Neumann entropy here, you might say, well, let's do tomography and then the rest. We would like to do better than that. Okay? And this again where these randomized measurements will come in the way that you will see afterwards. Again here, reduced density matrix. Let me point out that if I got a pure state over here, that this pi partition of the wave function here, we can always write down the total wave function as a pi partition into a part referring to A, and the other part referring to B. These are the A and B parts that we have over here. And you can see that in case that we have entanglement, there will be a whole sum where alpha goes from 1 up to chi. This is a Schmidt value, and we call this thing the Schmidt decomposition. And there will be a sum, and there will be weights in front. Psi alpha at the end will be the entanglement spectrum. But how many terms appear in the sum at the end will be kind of a quantifier of the entanglement that you have. So if chi is equal to 1, you can see this will be a product state. But if chi is larger than 1, then this will be an entangled state. And of course, methods like matrix product states very much built on the fact that if you write down the Schmidt decomposition, that this entanglement that you have, like for area law states and ground states, is very low. It's a small number, this chi, and then we can devise theoretical approximation. But of course, a quantum simulator can represent the highly entangled state, and so possibly states that we can never represent classically. So you can see that by learning what this chi is or what the Schmidt decomposition is, we learn about the structure, the entanglement structure of the many-body wave function. I will show you afterwards example that we measure, for example, the Schmidt decomposition, how it involves. And we have quench dynamics. In quench dynamics, we start with the product state, and then we have entangling operations that come from my native Hamiltonian. They will entangle that, so you will build up here a superposition state that corresponds to this Schmidt decomposition here. Well, finally, third part over here, there's another part here, which is the reduced density matrix. I can always write as an e to the minus h tilde a, and we call this quantity up here the entanglement Hamiltonian. You might ask at this point, well, this is just a rewriting, of this. I can always rewrite this in a particular form, and this looks like a Gibbs state that we know from thermal ensembles. But of course, it is not. This is just a rewriting of the reduced density matrix. And you might ask over here, what have we gained? Well, what we have gained in the following, and this will be very important, and this will be why this entanglement Hamiltonian will be the focus of one of our studies, and we will ask, can we measure the operator structure of this? That it turns out that for quantum simulation many-body systems, the structure of this entanglement Hamiltonian is much simpler than the structure of this rho A over here. So this is the reason why at the end this will be the object of our discussion, and we will ask, can we measure or can we learn the operator structure of this entanglement Hamiltonian over here, because it is much simpler, and this is sort of the starting point, how you get something which is a scalable way of learning this entanglement Hamiltonian for system sizes where maybe tomography that you might sort of try over here for the density matrix fails, but due to the simplicity of the problem, if you got many body interactions with local interactions and so on, this has a simple structure, so we can learn this sort of more easily. And that's very important if you want to go to this regime of quantum advantage.
So how can you distinguish that you're entangled and not equidistant in the environment?
How am I mean, by just looking at this thing over here?
Yeah, or is it...
Okay, well, I assume for the moment that this is a mixed state, okay? And the mixedness sort of is reflected in this Hamiltonian. If this thing was a product state over here, or just a pure state, for example, the situation would be much simpler, and then this Hamiltonian wouldn't really make so much sense. So the entanglement Hamiltonian is really sort of a meaningful quantity if you have entanglement in the system, because it characterizes sort of this mixedness, and we'll see that now on the next thing down here. Remember that on the previous slide I wrote down the Schmidt decomposition, and we had the Schmidt values over here, and now you can see that the eigenvalues, you know, of the reduced density matrix is just these Schmidt vectors that we introduced here before, and this chi over here, which was the Schmidt value, and these are the, you know, these different coefficients that we have over here. They're just sort of the eigenspectrum of this Hamiltonian over here. So the eigenspectrum of this entanglement Hamiltonian basically tells you what the Schmidt decomposition is and how many terms we have. And by asking the question, can we measure this eigenspectrum, you're sort of measuring then completely, you know, how many terms you have in the Schmidt decomposition. Okay, and so for us this is a way of sort of getting a hold of how we can measure, for example, the Schmidt decomposition over here in particular cases. Yeah. And so our goal at the end should be, you know, can we learn this and efficiently and you know, or sample efficiently. I will comment on this efficiency then afterwards. But my statement is that this structure over here, this entanglement Hamiltonian for many body systems with local interactions, very often has a very simple structure, and so we can learn it more easily, and this is sort of then the entrance point where we can then learn these things in a more efficient way than by other techniques, and this is what we'll demonstrate at the end. And of course, you always want to cite somebody famous. You know, Duncan Haldane, of course, was the first one to introduce this entanglement Hamiltonian in the context of topology. We'll not do topology now in the following, but rather I would like to show you, going back to my elementary example of frequency dynamics, what we mean by learning, you know, this entanglement spectrum, or what it means in the particular context here. So let me go to the problem that I said before. We had here ions, you know, you apply your native Hamiltonian over here. Initially you have a product state, so you prepare something like an L state. And then if you evolve in time, a certain amount of time, you evolve to a highly entangled state, and if I take my subsystem out, this is my reduced density matrix over here that I can always rewrite then in terms of this entanglement Hamiltonian. I would like to learn now here, for example, what my Schmidt decomposition is and how this build-up works from the initial product state to the highly entangled state. So I will show you now here the result, and we will afterwards talk how we actually got it, okay? But this will take a little bit later. So what we would like to learn is this, that we would like to see how these coefficients over here, at the very beginning, as I said, this was a product state, and the chi was equal to 1, how this then builds up as a function of time, that many of these terms are coming in, and we can see that by just looking at this entanglement spectrum, the build-up of the entanglement that we have in quench dynamics. And let me just emphasize also that, you know, if you see these things for a very long time over here, we would expect that if you wait a very long time, this system should actually thermalize, and the subsystem should thermalize. So in this case, you would expect that the entanglement Hamiltonian that you have over here would just become the system Hamiltonian for the sub-part, the sub-region that we have over here. This would correspond to the thermalized state that we have over here. So what do we get? I mean, suppose you are a theorist, okay, it's very easy now for 20 ions that we have over here to run a DMRG calculation and then calculate what the eigenspectrum is. What will you find? We are plotting here time down here, and now we are plotting here this lambda alpha, which is just this entanglement spectrum. And you can see that the time equal to 0, we have here that there's only one value which is equal to 1, and all of the other ones are 0. This is the indication that over here we started out with a product state. But you can see as time evolved over here, and this is the relevant Hamiltonian that we're writing down here, all of these, you know, eigenvalue spectrums are coming in, and at each of these points over here, at the end, you know, many come, and this is the region where you're approaching thermalization. We cannot really do this in the experiment over here because at the end, this is also a dissipative system. Decoherence comes in, where of course the analysis that we're doing here, assuming a pure state, might actually fail. So we have to adapt these things, and at the end, accounting also for decoherence. But let me see what comes out if you do our protocol that I've not explained to you yet. You can see that this is what you measure. So take a particular point over here in time. Okay, you can see there's a dominant value, then we have this whole spectrum of eigenvalues that you can see. This is the entanglement spectrum live, and you can see that this shows really the build-up of entanglement during the quench dynamics. And as I said, for very long times, these things should go over to what we expect, for example, from a Gibbs state, assuming that the whole thing actually thermalizes. So these are the kind of questions, you know, that we can ask in this context, and this is a quantifier of the entanglement that we have. You can also then measure, for example, here the entanglement spectrum. I will not really say much more about it. But let me now sort of start and go back to the protocols and start with something very simple. We ask the question, how can we measure Rayleigh entropies with, for example, randomized measurement toolbox? How do we do that? What are the physical ideas behind all of that? And then move on to something much more complicated, that we go for the real thing. That will be that we would like to do a learning of the entanglement Hamiltonian in our system, and then even demonstrate it in the experiment for a very large particle number, which in our case is 51, but in a real experiment, as I said. So again, take this now sort of maybe a little bit more historical roots, but I would like to start out with the Rayleigh entanglement entropy over here, for the very simple reason that this is sort of easy to explain what the whole concepts of what the ideas are, and then we go sort of more complicated at the end in the second part of this lecture here. So suppose that you decide, well, let's measure the Rayleigh entropy, which is really the purity of a subset. You know, I got my whole wave function, which I assume to be isolated. Now I take a subset out that I call A, and I'm looking now at the purity, you know, of my many-body wave function that I have over here. So this quantity is becoming less than 1. It's an indicator that we have entanglement in our system. And how can we measure that? So some of you might say, well, you know, you have here the reduced density rate squared, and you take the trace of the whole thing. The answer should be easy, no. So why not simply sort of do something like tomography? Because, you know, other techniques that you might sort of invent might fail due to the fact that this is a nonlinear function of the density matrix. And usually, what we always do in our quantum experiments is that we measure expectation value of some operator. So this is then this is not rho squared over here. Here's a rho squared, and this makes it sort of tough. This makes it non-trivial in what we do over here. So at that point, I might say that why not do tomography? I call this protocol 0, indicating that this is the last thing that we want to do, for the very simple reason that, you know, it is very expensive. So if you look at the subsystem size, you know, and it has, you know, the number of qubits there is NA over here. You can see that this is always exponentially expensive. So in practice, this means that if you go beyond 8 particles, you know, in an experiment, this is becoming very, very tedious. Rainer Platt at one point did tomography here with 8 qubits, and I think that it was 600,000 measurements or whatever that he took, you know, and at the end, of course, it was argued that this was maybe not sufficient to get the whole thing converged. And so this was sort of this is true, but it's not a very good idea. Of course, it's working for small system sizes, or, and this will be the main point in our following discussion, or we know something about the quantum state, where we put in knowledge that we have to maybe then test and also verify that we know something about the state, that we can make these things here much more efficient. But for the moment, we just, you know, take this thing over here. There's protocols where you can do that, and we wrote actually papers, you know, theory papers some time ago. For example, if you have the case that you are able to make 2 copies, you know, again, with the IS, it's not so simple to have 2 copies that talk to each other with a quantum channel. You know, if you are able to make quantum operations between these 2 copies, well, you can always rewrite the trace of the rho A squared that you have here, this purity, is something that we call the swap operator, because, you know, when I write down the 2 copies over here, this is something like rho, tensor rho, whereas over here we have a rho squared. This is, watch out the difference. Here's a tensor, and this is just a product. So we need an operator that converts, you know, the product over here into the one which is the tensor over here. This is a swap operator. This is indicated by these arrows that we have over here. And I give you a simple example here. You know, if I write down, sorry for calling it V over here, rho 1, tensor 2, if you apply this operator that interchanges indices, you just get the product of these 2 out down here. Well, if you do that, you can, you know, ask yourself, can we find a protocol that, you know, implements as a coherent quantum operation the coupling, you know, which is the swap operation between these 2 copies, and this can be done. You know, we wrote down papers about these things, and as a matter of fact, when I visited Harvard, I talked to, at that point it was actually Adam Kaufman a lot about these things. And at the end, Markus Greiner was even convinced to do an experiment. They did these Harvard experiments where they did quenches with Harvard models, where they measured all of that. And I have some proof of some of these protocols if you want to see that, but I'm not going to do that here. The main problem, you know, is this, that when I talk to my friends with ions, they say, sorry, I don't have 2 copies, so I come up with something else. Okay, so if you don't have 2 copies, like 2 trapped ions that talk to each other in a coherent way, at least easily, let's do something that we call virtual copies. So here's the trick of the story, you know. So I have 1 ion string, so if I don't have a real copy, I make myself a virtual copy. Okay, I have to show you how we actually do that at the end, you know. And you might tell me, well, we cannot do real copies, you know. In quantum mechanics, this is not allowed. But of course, quantum mechanics doesn't allow us to make virtual copies, so you will see that this is something which is a legal quantum mechanical operation at the end, what we do. And how do we now measure this thing down here? Well, the way how we can devise protocols based on these virtual copies is from statistical correlations in randomized measurement. And for us, this was sort of a few years ago, the real entrance point into the whole story, where, you know, quoting always Chan Howard always says, the signal is the noise. You look at the noise over here, and the noise sort of has the signal, which is then really the purity over here that we would like to measure in this context. Let me try to explain the basic idea, what is behind it. I explained it here in a form that was originally written by Stephen van Enck and Carlos Benaca. It cannot be done like this. You know, they cite a paper, let's assume that we have a universal quantum computer and that we go. Sorry, we don't have that over here. We only have quantum simulators that are not completely programmable. But it tells you what the idea is and then we can generalize, and the generalization is not entirely trivial, but let me get the point here first. So imagine now that I have a string over here of ions, and they correspond to spins, and I look at the subsystem that I call here A, and my reduced density operator I call here rho A, okay? So the first thing that I do in this randomized measurement protocols is that I apply a random unitary. Taken, for example, from a circular unitary ensemble. I just take it out from over there and I apply it to the system. And so at that point you will say, well, that's a pretty bad idea because you got your beautiful system and now you scrambled it up in a way which is sort of uncontrolled. You made a random unitary. Why can this be good? And of course, you know, once I've done that, I can make a measurement over here that I can read out a bit string in my standard basis corresponding to the probability over here, but of course the probability will remember the U that we had over here, which was the random unitary that we applied over here. Suppose now that you decide to do many of these experiments with different randomized measurements, and of course these probabilities will not contain anything interesting, they will all be equal, so this is just a constant. But the interesting part will be that if I take these probabilities and I square them, and afterwards I average over the randomized unitaries, then I get something over here, the expression which, wow, indeed contains something that looks familiar or interesting. It's a trace of rho A squared. And let me just give you the flavor of what's sort of behind this whole thing. You know, the flavor behind it is like this, that, and this has this interpretation of these virtual copies. You know, the probability is squared and then averaged afterwards. Well, let me write down this probability as sort of a trace of 1 and 2. And I write this thing under one trace, so I've doubled my system over here. You can see this is my first system and this is my second system over here. I've sort of extended the Hilbert space. Over here it was one system, and just taken this expression and now written as a trace 1 and trace 2, but put it now under one trace over here. And now we have U here, U dagger here, U here, U dagger over here. And those people that are familiar with Fick's theorems or Gaussian statistics and so on will immediately realize that, you know, there will be two kind of correlations between, for example, if you assume for the moment this is a Gaussian, it's not, but it's sort of something that's very similar, that you have, we call this here the two design property. There will be a correlation between this first U and this one here, but also then these cross correlations, and these cross correlations give rise at the end to the swap operator, which is exactly the Rayleigh entropy that we wanted to have. So randomized measurements are actually, you know, quite interesting, and every experimentalist, of course, likes to apply these things, except that these are unitaries, you know, in the whole subspace, and you might ask immediately, can we not simplify our protocol here? And this is, of course, what the experimentalists complain to us first. You know, you talk about generating here a unitary, which is acting in Hilbert space. How do you make that? Well, you can make it by using random quench dynamics and so on. We've done, you know, for Hubbard models, we've studied that. But a simple protocol would be the one where you only allow random unitaries that act on single qubits over here. I find it still actually quite amazing that the whole protocol still works in that case, and this is something that Andreas Ellman and also Benoit Vermeersch have done over here. You know, where you have here these probabilities and bit strings, but now these unitaries are simply products over here. And if you go through the whole derivation, you know, we wrote down formulas that basically have the following structure. You know, here's the probability for measuring one bit string, another one over here. And now you can see that we form a quantity over here, this would be Hamming distance, getting an estimate of a quantity. And if you repeat these things very often, you can actually show that this is trace of rho a squared. If you don't see this right away, yeah, the derivation is actually complicated, but I think it sort of gives you the idea, you know, what the whole thing is about. And to write it in a more appropriate form, we have here, of course, you know, n number of measurements, and then we have different number of unitaries. This is sort of the more complicated formula over here, and features local operations and measurement. And of course, you might ask about scaling with the number of unitaries and measurements, and I'll come back to some of these things later. So let's see if this works in an experiment, and this was sort of for us historically the first thing that we ever did in this case over here. We take our Ising Hamiltonian here, and the way that I described it before, all of these unitaries here, and well, you can see now that we can now make a plot over here where we plot these purities here. For this would be only a subsystem of 1 qubit. This would be the first or the second one. This is the 1, 2, 3, and so on, all the way up to 10. So this thing over here is trace of rho squared of the total 10 ions that we have over here, whereas the other ones are sort of, you know, smaller and smaller units of my subsystem. Okay, so we are plotting now the trace of rho squared, you know, for different subsystem sizes that we have over here. Well, if you do this first at the very beginning of your quench, you would expect this is a product state. This thing better be 1. Well, it's not 1 because, you know, there were some measurement errors in here. It turns out the total purity was 0.76. But the interesting part is now how it evolves during the quench dynamics. And you can indeed see that, you know, the point over here, that the total system that we had over here, the purity basically remained constant. You know, and this is what you expect if you have unitary time evolution. You know, but sort of if you divide the system into 2 parts, like over here, you can see that the purity here goes very low. And this sort of going low of the purity is just an indicator of the fact that you got entanglement in the system. So this shows you in the simple quantifier of the Rayleigh entropy, you know, how you build up this entanglement. This is a theory done with decoherence, and I can explain more. And if you plot it as a Rayleigh entropy by itself, really as an entropy, we see that this is sort of, you know, entropy 0, the pure state, and then it evolves in time, and you got this bell-shaped thing over here. The important point being that for the total system, you know, the entropy remains 0, or approximately 0, this whole thing. So the total thing remains a coherent wave function, a pure state wave function, where the subsystem becomes mixed. This is sort of the message. And you can do that for subpartition, you can add in these order strengths and so on. And at that point, of course, you can also say that, you know, what, you can do different things, like you can generalize these protocols. Like I take one quantum machine, one over here, second quantum machine over here, and a very similar protocol gives you now fidelities that measures the overlap of 2 different quantum machines. And you know, again, with the experimentalists, we had some data left over. We did some of these analyses, and I also want to mention that Chris Monroe in this group also had a paper that compared different quantum machines in this context here. And sort of as the final note on this Rayleigh entropy, you can also measure things like partial transpose. This is very easily, you know, added to the formalism. They have a subsystem AB over here, but you do a partial transpose of one of them. There's these things like these PPD conditions, positive partial transpose conditions, and you can write down inequalities between them, and you can test all of that. So all of this is sort of open up, and I don't think that there's much point in me going now in depth in this thing over here. I think you probably got sort of what the point is of what we're trying to do and how we achieve it. And this is something that works on today's quantum devices, like because the only requirement that we have is that we have single qubit rotations that we must be able to randomize in an appropriate way. And of course, Google has used the same kind of a protocol in some of their study, and of course, superconducting circuits have the big advantage of being very fast, okay? And so from this point of view, you know, being able to make many measurement runs or many repetitions is sort of essential. And, but it's kind of a tool that is now kind of standard, I would say. So in the lab, I mean, they just apply these kind of things here routinely. So I'm sort of at the point now of entering the second part of my talk here, where we get more greedy, and we would like to talk about entanglement Hamiltonian spectroscopy. A little bit appointed, so maybe there's a good point over here that if you have some questions that we can ask you now about this first. That was sort of the more introductory part here, and then we can move on from over there to sort of things that we're doing at the moment, and this will be, you know, the following topic. So, questions?
When we were talking about the entanglement Hamiltonian in the long time, where the subsystem thermalizes and you're able to replace the entanglement Hamiltonian with the Hamiltonian of the system.
But it's not replacing it. Simply the entanglement Hamiltonian becomes the, you know, Gibbs ensemble of e to the minus beta. Okay, H and H is the subsystem Hamiltonian that we write down in thermodynamics. When you took your course on statistical mechanics, you know what you do is simply you take the subsystem and you write down the Hamiltonian there. For the subsystem, there should be some boundary terms around it that we normally ignore because we say that we have some thermodynamic limit, that the boundary effects are small. This is what it is. So this Hamiltonian, the entanglement Hamiltonian, we expect for a very long time to become the Gibbs ensemble subsystem Hamiltonian that we know so well. But in the experiments, it cannot be seen because there will be decoherence from dephasing and so on. You know, the real system that's implemented is not the Hamiltonian alone, but there's also dephasing. You have to write down the Master equation, and then you're violating the rules of the game that we are playing, and then life becomes more complicated. And we can include some of these things, but notice that when I wrote down a Schmidt decomposition of my wave function, I assumed a pure state wave function. Okay, and this might not be true for these very long times. Okay, good. More questions here?
So in the Rennie entropy example that you showed, the initial state was not pure, but the time evolution...
Well, the initial state was pure because the initial state, we simply assumed that, you know, there was sort of our spins, our 20 spins or whatever we had, and we prepared them in a spin up, spin down, spin up, spin down product state. So in that sense, it was a product state that we had at the very beginning. And this was the reason why when we show this build-up, you know, of this Schmidt decomposition, seeing the different parts of this superposition grow. At the very beginning, there was all 0 and only 1 was 1. And then the other ones sort of, you know, came up, then forming this entangled state.
I see. I meant like trace rho squared was something like 0.7 even for like the full...
Oh, you talk about the experiment over here?
Yeah. So...
Okay, the experiment over here, you are asking why do you have here 0.76 and not 1? This is your question?
No, I mean, it's also like, why is it that the subsequent time evolution does not introduce substantial decoherence? I was just curious, like, why do we start with this initial decoherence? But
okay, so in the particular experiment that was done over here, the main error, and this was a very early experiment, and in the meantime, some of these errors understood much better. This was mainly a measurement error because there was some crosstalk and reading out the qubits. And this is the reason. So even though this is a product state, you can see that for a single atom, we have here 1 as it's supposed to be, okay? But you can see that it sort of decreases down here to this 0.76, and this is simply that each of these, when I measure 2 qubits, 3 qubits, you know, this is like this measurement error to the exponential. And this is exactly what you can see over here. So this is doing wrong measurements at the very beginning, but it's still a pretty good product state. And so these are experimental artifacts here. But the underlying state is a product state. Okay, good question. More questions here?
Yeah, for reference, how many randomized measurements do you need to take, and how does that scale with the...
Okay, I didn't, that's a very good question, of course, you know, and so the number of measurements was typically, I don't know, 150, and then you took the same different unit areas maybe 100 times, or something like that. I will talk about the measurement budget a little bit later, but it's a very important question, of course. In particular, for example, it turns out that in the context of the Rennie entropy, we said tomography is very expensive because it really scales exponentially. It turns out that the way that we do over here is still an exponential, but it is a much softer exponential. So we can do much, much larger system sizes, but in the end, we also run into a problem, which is that it is exponential, even though more friendly exponential. And we have some other ways to replace that. Okay, so the quantum protocol I showed at the beginning with the 2 copies did not have this problem. Okay, but if you want to do it sort of with classical communication instead of quantum communication between the 2 copies, we made virtual copies, but it was at the end sort of classical correlations that we had. This is the price to be paid. But I come back to this point later when we talk about the entanglement Hamiltonian at the very end of the second lecture. Okay, but it's a good question. More questions here? Then you want to make a 5-minute break to recover, or should we just go on? You're too tired to answer.
Let's take a 5-minute break.
I think otherwise we have too much fun here discussing in person, and also back to the serious part. Okay? So my original plan actually for this lecture was that in the second part I wanted to talk more about randomized measurements, sort of in more general context, in particular, with John Prescott and friends. We wrote this review article. We called it the Randomized Measurement Toolbox. It came out in Nature Reviews just I don't know, half a year ago, something like that, a little bit more, which summarizes many of these things, coming sort of from the side how we develop these things, and then of course there's these classical shadows that are really a brilliant idea, and in particular these classical shadows come with quantitative estimates that we in our analysis originally did not have, to estimate how many measurements does it take in order to. This is condensed, so we were somehow complementary what we did, and we put it together in one review. So for us, the key papers that I talked about now before are these ones over here. And the classical shadow one, I mean, the really famous one is the one over here, and these are people on the right that did these things. And as I said, we sort of had experimental data from over here. And the great thing about this classical shadow is to talk then about, how many measurements does it take in order to, and then the whole story starts, and then this is really what the content is. Let me sort of do now something a little bit different that maybe goes more coherently with the story that I told you before. I would like in the following now take these randomized measurement ideas, but at the end what we want is to sort of talk maybe more about the physics per se and what we're doing here with quantum simulation. And I would like to speak about entanglement Hamiltonian tomography. Okay, this is something very interesting.
Sorry, before we proceed, do you mind if can I ask a question about the previous section again? There was something that came up during break.
Sure, yeah.
Could we return to the plot that shows calculated purity versus subsystem size from 0 to 10?
Yeah.
And to clarify, what were the different series describing? The 5 series, I think, from 0 to 5?
Okay, so you're simply asking, I'm showing here data points, and I'm showing also that come from experiment, but there's an underlying theory, and what kind of assumption did we make with the theory, right?
No, I'm just asking right now, really simply, what are the series representing? Is this time evolution? Like the length?
Okay, sorry, yes. So this is different time. This is time equal to 0 up here, these black dots. Wait, let me go back here. These black dots, this is time equal to 0. The time equal to 0, we prepare a product state, an L state, spin up, spin down, spin up, spin down. It's a pure state, so we better get, for all of these things here, 1. Okay, because radial entropy pure state is supposed to be 1. It's not 1 over here for the total system because there's measurement errors. And now we turn on the time evolution. And what you can see now is the time evolution. It starts now at different times. And this simply shows that, when I have my total system, it's supposed to be still in a pure state. And indeed, you can see over here that the right-hand side over here, well, we got 0.76 at the very beginning, which I said was a measurement error. But during the time evolution, this doesn't change.
So if we had longer time evolution, though, we would expect more decoherence, right, for the subsystem size 10.
You would expect, there's a little bit of change over here, but it's sort of, a very minor change that things are sort of getting worse, but I would say,
does this imply that, like, measurement error
The measurement error was the dominant part in this particular experiment.
Okay, so
this has some historical reasons, whatever, and this is what you can see over here.
So if we have perfect measurements, then we would expect actually more differences between the series data at point 10, right? It would be 1 and then...
But if you have no measurement, in preparation, whatever, no decoherence, then you would expect that the right-hand side should always be 1.
Okay, and then if we added in decoherence, then you would see...
And if I add decoherence, then it goes a little bit worse, okay? So you can see over here the decoherence is not really so bad. The main error over here was the experimental measurement error.
So really spam error is actually a key concern when computing purities.
Yes, okay. Don't forget, this is a more historical experiment over here, okay? In the meantime, they are much better. And it turned out that they got actually some wrong random unitaries in there. This was in the early days. And so there's a lot of things that in the meantime are done much, much better than what you can see over here. Okay?
Wonderful, thank you so
But I think that the main message or the point is really that if I bipartition the system, you can see that the purity over here is pretty small, and the purity becoming here small and getting smaller and smaller as a function of time evolution. This is the indicator or the quantifier over here of the entanglement build-up, during this quench dynamics. But you're right, probably also you were saying, that there's also some decoherence part in there. But decoherence relative to the coherent part is on the level of a few percent. So it's a dominant part. And this is sort of still early in the game. We would expect that if you go very long times, it would be thermal and so on, but we cannot go into this machine. Okay?
Great.
Thank you. Good question. Yeah. Okay, so my plan was to talk about these things over here. In particular, I don't talk about that. But let me sort of move on and sort of continue the story. We really would like to do an entanglement Hamiltonian tomography, and we would like to do it in a regime that is not accessible to standard tomography, because we would like to go to very large system sizes, hopefully in a way that at the end might even work in some regime of quantum advantage that we have in our simulator. Of course, this will take a long time, and there's a lot of things to discuss, but we want large particle numbers where tomography fails. How do we do that? And so let me start out by briefly summarizing now, what we have with this randomized measurement, how we see that, and then we move on and talk about an excellent experiment that was done recently. So the sort of general concept of randomized measurement is that we have here, I draw it like, well, there may be a quench dynamics, there could be a VQE circuit, whatever you did, dynamics over here, then you got your wave function. You apply here unitaries, it could either be global unitaries, they could be local unitaries, as I described now just in the previous slides over here. You got your bit strings, and the story that always sort of goes like this. You got your quantum mechanical probabilities for a given unitary. You have your bit strings that are called here S and S prime, and then you have here a classical cross correlation of these different probabilities over here. Notice, that this could be an experiment 1 on day 1 in lab 1. This could be an experiment on day 2 in lab 2 over here. So these are the quantities that we're interested in, and the Rayleigh entropy was a particularly simple example of all of that. And then using the fact that we got a circular unitary ensemble, these things like 2D signs are coming in, and so on. This is sort of these cross correlations. One part is quantum mechanical, but this average that we have over here is really a classical average. And for this classical, at the end, we pay the price. If you replace this by some quantum correlations between the two copies of the systems, it will always be, of course, at the end, more efficient. So this is sort of a hybrid classical quantum protocol. The reason why it's good is that we can do it today in the lab. Okay, so we wrote a bunch of papers, that are listed over here, and I decided now to pick out one of these papers over here, which was on this entanglement Hamiltonian tomography that developed in 2 stages. There was a theory paper. At that point, we didn't have any experimental data. Then we went convince the experimentalists to try some of these things, and this is what I would like to show you now in the following. And this is this measurement of the entanglement Hamiltonian. So let me give you the story behind it. And maybe I should go back first by telling you, well, the slide that I had here before was about the Rayleigh entropy, and then there was a corresponding formula over here where these are these probabilities given the U. U was the random unitary, this is a random variable, and then this is sort of an estimating over here our purity over here. This was our formula. And it's actually very simple, to write down now a formula where you would simply say, oh, can we actually estimate the whole density matrix? So at that point, we're sort of doing a randomized tomography. We are doing here basis measurements in a random basis. And there will be a very similar formula over here. You can see this is an operator now over here that we estimate by having a certain number of unitaries over here. These S and S prime over here are just measurements that we are taking over here. There's this part, this is the, S is the vector that would correspond to the projection that we get over here after our measurement here. U is the unitary. This is becoming very much related to shadow kind of things that John Prescott and Al wrote down. And there's an identity that sort of looks like that over here, okay? And if I take the average, I get this thing out. I mean, of course, at that point, I'm caught, again, in what I said before. Tomography is exponentially expensive, okay? But I also made a remark before, if you know something about the quantum state, and we know we are doing quantum simulation, and the wave functions that we get from quantum simulation, they are derived from a Hamiltonian that can be quasi-local. The Hamiltonians are very simple. This is putting in this knowledge. If you try to put in this knowledge and combine it, with these sort of expressions that we have over here, we might be able to get something which is then an efficient, and I have to explain the word efficient, entanglement Hamiltonian tomography, that we are learning, sort of learning in the sense of machine learning, the operator structure of the entanglement Hamiltonian, and this is the kind of game that we play now in the following. And so the goal is now to learn the operator structure by saying that we know something about this thing over here. It has a certain form, that maybe only a very simple operator structure, and then combining these things from here, the measurement data that go in here, and comparing it with here, we might be able to learn this entanglement Hamiltonian. That's what we are going to do now here, the following. Okay, so you can see there's no free lunch here. Okay, no free lunch. Okay, but that's what it is. Okay, so in that sense, I've taken out a paper that we put in the archive now a little bit of time ago, and these are the various people involved here: Christian Kocher, Ludwig van Beinen, the theorist, and Manoj Joshi was the experimentalist, key experimentalist, and this was done in this 51-eye simulator in the lab of Rainer Blatt and Christian Roos, as I mentioned earlier. Okay, that's the lab again. Then you see that we talk about real experiments over here. Now comes the story. So I give you first an outline of how you really design an experiment, and how you then decide what you would like to see, and raise certain expectations, what you can see, and then based on that we will present an analysis of this entanglement Hamiltonian tomography. So we are sort of halfway through actually in preparing the whole story over here in the following sense. So I told you before when we talked about the variational quantum Eigensolver, we mentioned before that, one day you wake up in the morning, you say, today is the Heisenberg model, okay? And we write down our circuits, we test them, and we prepare the ground states. We get 2% of the ground state. We never get the real ground state, but we don't really mind. 2% is pretty good already. And this is the stage over here, where we have 51 ions. We have the subsystem over here. And we would like to learn then at the end this entanglement Hamiltonian that we talked about over here. So we would like to do a complete quantum state tomography of a subsystem. And the subsystem sizes at the end are supposed to be something like 20 or even larger, so they're really large. So forget about tomography, okay? Yeah, so large subsystem sizes. And we want to do it by not measuring rho A, but measuring this H tilde, which was the entanglement Hamiltonian. Here is the Hamiltonian that we wrote down at the beginning, and let me visualize now what we are going to do. So we have here entanglement properties we are after. Here's sort of a pictorial illustration, don't take this too literally, of the energy spectrum of the Hamiltonian up there. There would be the ground state down here, and there's what we call it the unheated state. So ideally I would like to prepare a single ground state. Ideally I would like to prepare a single excited state. We cannot do that, but we can prepare superpositions very close to the ground state, and you can see that by this bracket over here, and we prepare states that are maybe, I don't know, 15% of the total energy spectrum, 50%. So we might look at it like a microcanonical ensemble, sort of like, but it's not really, because it's a coherent superposition of these states over here. And then you would like to study now the entanglement properties of these states by fully characterizing, this why it is entanglement Hamiltonian or the whole density matrix. So what kind of things will we be after? Well, the first thing that you might sort of know is this, that if I have a local Hamiltonian, and I go to the ground state, matrix product states and all of these things make their living from the fact that for these particular Hamiltonians that we have, the ground state, you have simple quasi-local interactions and all of that, we have area law entanglement. So very little entanglement. your little entanglement, you can do classical computations based on that. If you go up to to highly excited states over here, this would be, by the subsystem, would be a thermal state, that we pick out over here, this region A. Then, of course, you expect volume law entanglement. This is what you learn in your course on statistical mechanics or thermodynamics. The entropy scales, like the volume of the whole thing, and not like the area, the surrounding volume. So these are things that can be seen in an experiment. We would like to do that actually with this Heisenberg model. I'm plotting here sort of a quantum phase diagram. You can see that if delta is equal to 1, so this delta is this thing back here, so all three terms, xx, yy, cc, have here the same magnitude. This is a critical point here, delta equal to 1. Actually, this region, the conformal field theory, is valid. We'll see why I'm saying that, because of the following repeat of conformal field theory to give us a good guess for what the structure of this entanglement Hamiltonian is. Over here we have an antiferromagnetic phase, and we will look at 2 points, 1 and the 1.7 that we have over here, and we will ask these questions about area law, volume law, but then really the complete tomography of the whole state at these 2 points. Okay, this will be our setup. Okay, and this part we already did. We sort of have here state preparation and analysis. We can prepare the ground state. I already showed you. We can also prepare heated states. I will tell you afterwards how we got these states up here. Actually, in a very primitive way, but just applying the cooling circuit here once again. But before you scramble up, no attempt here to produce a single excited state or whatever. We just want something which is a little band up here, like a microcanonical ensemble. And then we would like to run our protocol over here. You're taking data for the subsystem over here. And what we would like to do at the end is to get then the entanglement Hamiltonian out from these data. So this is data, we have classical post-process, entanglement Hamiltonian. And of course then we would like to do these things to find out, for example, volume law, area law, entanglement, but really then the whole density matrix over here parameterized by the entanglement Hamiltonian for large system sizes. This is sort of the experimental scenario that we have in mind. So the left-hand side we already talked about, except for this protocol over here, down here. And the right-hand side is sort of more asking the physics question that we want to see. And I really emphasize that what we do now here, the following. This is, you could take other platforms, you can 2D systems and so on, other Hamiltonians. So what I tell you is rather generic. So don't take it, oh, this applies to ions only in 1D and so on. This is rather generic statements, okay? This is what I want to do. Nothing in life is ever completely generic, but you will see the following in what sense I mean that, okay? So we already have cooled it down. We got this thing, I talked about that before, we can move on. So let me now say a few things about learning the entanglement Hamiltonian and how we do that. And I had before, this statement that, well, we got some measurement data, for example, from randomized measurements over here. And we would like to find this entanglement Hamiltonian over here. And we concluded before it was expensive, except for small system sizes. Well, we don't have small system sizes here. Or we know something about the quantum state, and I mentioned before, we know something about the quantum state because we said we're doing quantum simulation, and our Hamiltonians have a very specific structure that generated for us the particular entangled state that we wanted, like the ground state, so that is heated state. So this state remembers, the Hamiltonian that was generating it. Okay, so do we know something about the structure to make this tomography efficient? Okay, and one notice over here, there have been papers, actually this is parallel to this nature physics paper I mentioned from our group, by Anshu here. They have something called sample efficient learning of interacting quantum systems, and they simply say if I got a Gibbs state over here, this is a Gibbs state, and they see this is by definition a Gibbs state over here. If this Hamiltonian is a simple physical Hamiltonian that has only 1-body, 2-body interactions, but not 10-body interactions or whatever, this Hamiltonian learning can be done efficiently. So there's mathematical proofs, that if it is a Gibbs state of a Hamiltonian, which is a finite operator support, then we have efficient algorithms for doing that, okay? And this is sort of what we're now relying on the following, and this is the basis of what we do. So what do we know? Okay, so at that point, I appeal to a theorem that I'm pretty sure none of you have ever heard before. This is from very mathematical corner of the physics Hilbert space, from quantum field theory. It's called the Bissiniano-Wichmann theorem. and I will give you a very simple explanation. You know, theorems always come, you know, if I assume this, this, and this, then the outcome is that, okay? And what this theorem tells you, but it is a very general and very generic theory, and remarkable, you know, in its own way. I mean, every time I look at it, I say it's amazing that this is true. It says the following. So, the theorem was derived by people working in relativistic quantum field theory, which means that we have Lorentz invariance. So notice that there are certain symmetries that are behind the whole story. You know, you make assumptions about symmetries. This is key to the story, you know. You have to ask us at the end, is this really true or not? And when you write down a Hamiltonian, you know, I just write this for 1D, but actually the theorem is valid in all dimensions. If you write down a quantum field theory, this is your Hamiltonian density that you have over here. Can be a very complicated interacting system. It could be integrable, non-integrable, whatever you want, but it should be a relativistic quantum field theory with a Lorentz invariance that we have over here, okay? And let's look at something that most of us will find out very interesting, the case over here, namely the vacuum state, that asks about entanglement of the vacuum state. At the end, we're going to rephrase this thing as a property of a many-body system, where this thing will be the ground state of an interacting many-body system, you know, when we rewrite it. But for the moment, this is, we ask about the entanglement structure of the vacuum state of a relativistic quantum field theory. Illustrated in a simple way, you know, if I take a 1D system for the moment, it is valid in higher dimensions, and I bipartition into A and B, the statement here is a remarkably simple one, namely that the trace of over the system B over here, we want a reduced density operator from this part over here, of the vacuum state, the ground state of my system, is simply an exponential, and it has the form of a Gibbs ensemble. You know, if this beta over here, this inverse temperature was a constant, you can pull it out of the integral, then this thing would be the, would over here simply be the Hamiltonian, you know, the one that we wrote down over here. Then you can see this would be the Gibbs ensemble for a given temperature beta. But the statement of this theory aim is that the reduced density matrix has the form of a Gibbs ensemble, however, with a local inverse temperature. Okay? So beta becomes dependent on X. How does the beta over here go? Well, the inverse temperature over here that you have is very hot, which means that beta is small at the cut over here. This means that, you know, if the temperature is very hot, then it means that this state, think about it, locally very, very mixed. But it's kind of clear, you know, you got entanglement over here, and if you cut it in the middle, you know, there will be entanglement, so it will be very mixed and very hot over here. And this theorem sort of implies here that if I'm moving away from this cut, you know, there's a linear ramp, this beta, and so this temperature, this inverse temperature, has a very, very specific dependence, but otherwise it is a very generic statement. So we have very remarkably here an expression for the ground state of a relativistic quantum field theory, that the reduced density operator has the form of a Gibbs ensemble, however, with a local inverse temperature, which is very hot at the cut and then cools off once you walk away from that. Okay? This is theory. Okay, not much to argue. So in other words, you know, we can identify this object that we have up here as the entanglement Hamiltonian, because, you know, we get now a prescription over here that simply says, if I take my original Hamiltonian and I, you know, deform my Hamiltonian density over here with this ramp, which is this Pisuniano-Wichmann ramp that you have over here, so it's simply telling, having the Hamiltonian and multiplying it by ramp. So what this theory tells us is that the entanglement Hamiltonian is nothing than the original Hamiltonian, but locally multiplied by a ramp. Can't be simpler. Right? Amazing that this is true. I mean, you know, for any interacting system. But of course, don't forget, it comes with the symmetry, and the symmetry is, of course, a key deriving all of that. There's some references here, in particular, if you want to read about this, there's this review by Marcello, who wrote about these things. If you add now, go to conformal field theory, that I mentioned before the relation with the Heisenberg model, we have, of course, adding scale invariance to the system, and this allows us, this is these papers by Cassini, you know, if I take a part of the system out over here, you get the same result, but now this inverse temperature has the form of a parabola. So, you know, it's beta is 0 at the two edges, very hot there and very entangled, and if you move away, it gets less and less, and then it gets on the other side, again, very entangled. You know, this is what the statement is. Very pictorial and so on, and now you might say, well, it's not true over here to take a lattice system. This doesn't apply to a lattice system, but why don't we apply it nonetheless? You know, sort of in an approximate way, and you know, you would simply say that if I got now an interacting many-body Hamiltonian, that where maybe the effective field theory is sort of, you know, for emerging for very low energies, something which is a relativistic quantum field theory, then these things should somehow approximately true. So this means that if I write down this entanglement Hamiltonian, it simply means that we got kind of a recipe. Take the original Hamiltonian, multiply it by beta L, and beta L, for example, over here in this conformal case, would have the form of a parabola. You know, so we have a very simple prescription that conformal field theory suggests that the entanglement Hamiltonian is simply the original system Hamiltonian multiplied by a parabola. Okay, that's an hands-on idea that we can test first of all theoretically with simple calculations, in particular 1D, but we can also try to see then this provides a reasonable ansatz that we can try in an experiment. And of course, it is very important to realize that when we do that, you know, that we have here maybe additional terms that we have to test if they are there or not, you know, so this is not an exact theorem in the particular case of these lattices. So to zero order, this may be true, a parabola, but we really want to see that, plus maybe corrections over there. It turns out that we never see these corrections because they're too small. You can test this first of all, you know, in analytical models. There's many analytical models, like if I take the standard Ising model with nearest neighbor coupling, it turns out this is an exact analytical result that comes out. Quite amazing, you know. Then you can also do numerics. You do the ground state of a system, you know, like Heisenberg. I talked about Heisenberg before. You see that beautiful parabola, you know. So this seems to be that the structure of the entanglement Hamiltonian is very often rather simple, you know, and the density matrix would be very complicated. So the second point of the story is that this sort of now is maybe the missing element in our whole discussion, because it provides us with an ansatz that we can try, but we should also verify at the end, you know, if indeed the ground states or approximate ground states that we generate have a structure of the form which is suggested by this very fundamental theory from quantum field theory. And this now starts the story, of course, that we have here a many-body system. Again, you can see my spectrum over here. Let me sort of guide you now through the expectation, then I can show you results. So I showed you before, this is the model that we want. We have here a critical region, you know, where conformal field theory is valid, in particular at this point over here. We will pick this point afterwards, where we would expect that these things should be valid, and then we will walk away into the gap region over here, where these theorems are not valid, but we will nonetheless try it. And as a matter of fact, in some cases, there are some analytical results that also indicate the validity there, but in a different form. So, but I would like you to think about the whole problem now in the following sense. So, we are doing an experiment, and we prepare first the ground state. Well, it's not the real ground state, but an approximate ground state, and the excited state, but not one. It would be very hard for these large systems, but something which is maybe more like a microcanonical ensemble or some superposition up there. Okay, for the ground state, as I said before, we have here area law. If you have a conformal field theory, there would be a log correction over here with a central charge that goes in front. In the case of the Heisenberg model that we discussed, the central charge is 1, so it turns out that this is a pretty small correction. In the experiment that you're trying to figure that out, you find that the error in measuring the central charge is about 10%, so it doesn't really work so well over here because it's a small correction. Up there we have our volume law entanglement that I mentioned before, like we expect for thermal entropies. So you can see that these volume law states, they occupy the largest part of Hilbert space over here. There's this area law space, they live in the little corner. And of course, it also comes with a comment that this is why classical tensor network simulations work, okay? And up there, volume law entanglement it can be too large to be represented classically. And, but quantum simulators can, of course, do that easily. You know? Okay, so let me now discuss this a little bit from the point of view of the eigenstate thermalization hypothesis, and don't take this too literally. This is sort of more to generate a little bit of feeling, you know, a physical feeling of what's going on. What does this thing say? So if I got prepared a single eigenstate up here, which we do approximately, and I take my system and I take a certain subregion out, like I did before in my discussion of conformal field theory, then eigenstate thermalization hypothesis tells me that the expectation value of some observable that lives in the region down here is basically the same as having a thermal ensemble, with the Hamiltonian over here restricted to the corresponding subspace that we have here. And so this means that we would kind of expect that the reduced density operator, that in the thermal region over here would be my system Hamiltonian, but now restricted to A, and of course there will be boundary terms and the rest, but we are going to do these things for very large subsystem sizes, so the boundary terms we expect them to be sort of under control, and you will see them afterwards actually coming up, what we have there, boundary terms, and you can see that I can of course always rewrite this thing as an e to the sum. Can you see I'm writing this thing as a beta I hi, this is exactly a deformed Hamiltonian. So if you have one temperature, this is a thermal state, this beta I that I'm writing over here, they are constant. For the ground state, they will be parabolas. Okay, this is my parameterization that I would like to show you now on the right-hand side over here. So this is my local temperature profile. So you can see that on the right-hand side, if this thing is a thermal state, I would expect that my reduced density operator has this structure over here, where these beta I, these inverse temperatures, they are flat. We have a flat temperature profile. There's one temperature in the whole system. This is flat over here. And this is an indicator of these thermal states that you have up there. And I can do that for different subsystem sizes. And if you do that, this is exactly, of course, then like a thermal state. Thermal states have volume law entropy in the 1D system. This means linear and LA. So we would expect to see a scaling of the von Neumann entanglement entropy as a function of my subsystem size that goes linear in the LA. Volume law entanglement. This is our expectation. Okay, provided we're able to measure this thing. Okay. What happens now if you cool? Well, I already gave you the answer. Before we talked about relativistic quantum field theory and ground states. And now we have here a many-body system, and we look at the interacting ground state of our system. Here, Heisenberg model, which by the way is integrable, so that's an interesting thing what integrability actually brings. Again, you might say over here, well, let's make an ansatz and represent these things here with the local temperature. We expect from Bissiniano-Wichmann or from conformal field theory, there should be a parabola over here. Again, this would sort of go like that. And we would then sort of expect as the outcome that we would like to see in the experiment that we have here maybe a logarithmic correction here at the critical point. Correction like this, and sort of here, you can see again what I said, this is very mixed over here at the boundaries, and cold in the middle. This is exactly the profile that you would expect for the reduced density operator with the local temperature that you have over here. Okay, this is what you expect. So these are, and don't be misled that this only works for iron in 1D, and for the particular model, these are very, very general statements that have to do with quantum simulation. So we're not after to be in the corner of whatever. No, these are rather universal statements. Okay. So what's interesting is that if you move away from the critical point, you would say a priori, well, conformal field theory is no longer valid. There's some exactly solvable models around, like for free fermions. What they show is this, that the same thing is still true, but the structure here changes. For example, this is sort of more peaked, like more triangle type. If you ask me why, well, this is how it comes out. We'll see that afterwards, as you can remember that. So now let's slowly come to the point. So we have our Heisenberg model, we have our sort of phase diagram here, central charge equal 1 conformal field theory, this region over here the antiferromagnet, and then let's go to the point delta equal 1 over here. This is now our ansatz that we make for this Hamiltonian. We can add additional terms. This is simply a deformation of the original Hamiltonian over here, where we just multiply local temperatures over here in front of this whole thing and put this into the ansatz. So this is sort of the ansatz that we have over here. Notice that what we're doing is that we're doing entanglement Hamiltonian learning, like the one of a Gibbs state, but not the one that Anshu had with a constant temperature, but it is something where you really are after the temperature profile. Okay, this is what we do over here. But first of all, you do yourself a little theory, and convince yourself that it works. And indeed, for the excited state, this is pretty flat. At the boundary, doesn't work so well. But as I said before, boundary effects are there. This is what you expect. You can see beautiful parabolas, and then you convert these things. Knowing now the density matrix, we can see that this is the logarithm over here, and this is the volume law entanglement. This is theory, okay? And now you compare now these sort of ansatz that you get, with a real DMRG calculation, and the fidelities that you get over here are actually amazingly high for these system sizes that we consider over here. At the end, they go much larger than the 9s that you indicate over here. Let's go to the lab. We already cooled to the ground state. This is a circuit over here. We can do some data taking over here, and I will tell you now the details of how we do the entanglement Hamiltonian tomography just after that, after showing you now results. What do we get now? So this is preparing the ground state. What do you expect now at these 2 points? This is a critical point, and this is walking away from the critical point. And now what we're showing here is the von Neumann entropy that we are able to measure now based on things that I explain now in a few minutes. You can see this is pretty flat over here. I would call this thing an area law. Yeah, I think it is. Yeah. We can at the end go to subsystem sizes more than 20. This is on the next slide over here. What is the underlying structure of these inverse temperatures that you can see over here? Can you see the very beautiful parabola over here? Where we take as fit parameters these individual inverse temperatures that we have. We can add additional terms. Here, you might be concerned about the fact that this is an integrable model. We have to add some chemical potentials. It turns out that they are zero. I just recently also saw a paper that argued that this should be the case. So these are results we get, that if you move away to the point 1.7, where the whole theory should no longer apply, still seems to be true. Well, in some examples, the same thing, but it's sort of more peaked over here. This is what expected from some analytically solvable models that we have. What happens now if you do something very primitive, namely